In this video, I would like to talk about reverse ray tracing, a technique often used for infrared optical systems. Let me show the fundamentals of that. I'm using the fundamental equation of radiometry. Look here at a Lambertian light source and a detector, and let omega be the solid angle under which the source is seen from the detector. I introduce another quantity, the so-called projected solid angle, which is omega times the cosine of theta, which is the angle relative to the normal of the detector. We wish to determine the irradiance on the detector, and the solution is given by this fundamental equation. It is the projected solid angle times the radiant excitance of the source divided by pi, where the radiant excitance m is the flux per area. Now it's only a matter of determining this quantity, this projected solid angle, and we will do that by reverse ray tracing, which means an interchange of the roles of source and detector. In reverse ray tracing, the detector is made a light source, a Lambertian light source with a flux 1. And the source is now made a detector, and it receives a flux phi ds. And it's the ratio between the projected solid angle of the light source divided by the projected solid angle of the entire hemisphere, which is pi. When I insert that in the original equation, I find that the irradiance on the detector is just this flux determined from reverse ray tracing times the excitance of the light source. This method can be easily generalized to more than one source and more than one detector. And the argumentation holds even if there are optical components in between source and detector, such as the simple example shown here. Here we have 4 light sources. We have a lens imaging them onto a pixel array. Now let's do everything with RayJack ONE. So here I have set up a normal ray tracing calculation where this is the lens as shown in the previous slide. And here I have the detector to which I attach an irradiance detector. And here I have created the light sources, Lambertian light sources, which I call dot 1 to dot 4. They are assigned an excitance of 1, which is the default. Here it's 2, here it's 3, and here it's 4. Let me show you the system. Here you see the light sources. Here you see the pixel array. And now continuing, the simulation gives this irradiance on the detector. And you see light goes from here in that direction. I made the simulation before with a larger number of rays, and then it looks like that. And here you can keep in mind the irradiance is something like 4 times 10 to the minus 2. Now let me turn to reverse ray tracing. And we set up everything as before, but now the light sources are modeled as planes which receive light from the detector, which is now the light source. And to attach the exitances of the light sources, I use here this command, reverse at excitance, 1, 2, 3, 4. The detector is here implemented as a reverse detector. And actually what I did is I spent roughly half an hour to write a script that makes such a detector. And what happens under the hood is I'm using a so-called user distribution detector, which does all the work for you. And it's really not very much. So let's simply start this simulation. And you get the irradiance. And here you see now that the light source is the detector, and some of the light hits the original light sources and then gets evaluated. Let me here look at the final results with a larger number of rays, and here you again see that except for a little bit of statistical noise, you end up with the same irradiance as before. Now, seems to work. In infrared optics, the excitance is often the thermal radiation of the of an object, and of course, RayJack ONE offers the infrastructure to calculate that. It's the class black body, and where I can here choose in-band excitance. And here I select a temperature. Let's use maybe 150 Celsius, or let's use Kelvins, which is the default, 450 Kelvins. And the wavelength range, the wavelength band here is maybe from 4 microns to 8 microns. And finally, I print that excitance. The result is given in watts per square millimeter, because millimeters are the default units. So this way you can now assign temperatures to objects and do thermal simulations. You may ask, when is it better to use forward ray tracing and when is it better to use backward ray tracing? I think it simply depends on statistics. If you need much more rays for forward ray tracing, because, for instance, your detector is small, then it will be better to use backward ray tracing and vice versa. Thank you.